Take a look at this spinning bicycle wheel as it gradually slows down. Notice how the positions that are closer to the center are more in focus than the points that are around the outside closer to the rim. That is because the points that are closer to the center are actually moving more slowly than the points near the rim. They actually all have the same angular speed, but there is a difference in the linear speed, which is what allows us to see some parts better than others. Let's take a closer look at this on a diagram. So point A represents a position on the wheel that is closer to the center. Each position on the wheel has to travel through a circular path, along a circular path, but if we compare this point to a place that's closer to the rim, we can see that point B has to travel a much greater distance, but in the same amount of time as a position close to the axis. And this explains why we were able to see the spokes closer to the axis more clearly than the ones further away. The points, again, actually have the same angular speed, but their linear speed or tangential speed, those are different. B has a larger tangential speed, even though it has the same angular speed, because point B must travel a larger distance in the same amount of time as A. Let's define some of these terms that I've been using. So the tangential speed or linear speed is talking about the distance that a particular point travels per time interval. And that is just a speed like we talked about before, so we will use v to represent it. It'll be measured in meters per second, and to calculate this, that's what we'll be thinking about, is how far does that particular point travel in a certain amount of time. The time, though, is the same for every point on that wheel, and that the time it takes a particular point to go one time around, one rotation, one revolution, that is something we call the period. Notice that we use the symbol T for the period, but it is a capital T. That reminds us that it is a very specific value of time, not just a general value of time. We can also think about this period as the time for the position to sweep through 2 pi radians, one complete revolution. And we'll see that idea in some formulas in just a few minutes. Let's take a look at this idea in action in a particular situation. So this is a demonstration video for marching bands, for a band as it's trying to go around a corner. So each of the X's represents a person, a marcher, and you can see how the groups do stay together. The one on the left is the way you want to be doing it. The person on the outside actually has to travel a greater distance in the same amount of time than maybe someone over here does. So the marchers need to maintain a consistent angular speed while having very different linear speeds, and that's what makes it difficult. That's why you can see the group on the right is not quite doing it the way it should be done. So an important difference to point out then between the different locations on a rotating object is the radius. Okay, that's what we'll call the distance from the axis point or the rotational axis to the location we are studying. So the radius, the r value for point A here, is smaller than r for point B, and then similarly the linear speed for A is smaller than the linear speed for B. Let's see if we can come up with an exact relationship between them. So we'll use these two ideas that the linear speed is different, but the angular speed is the same. So the linear speed is different because in a certain amount of time, which again we'll focus on one rotation, so that requires time capital T, the period. In that one amount of time, the object has to travel completely around the circle or the circumference. So that would be 2 pi r. But every point on that rotating object travels with the same angular speed omega. And so since angular speed is the change in theta over t, and they all travel 2 pi, one complete revolution, in that period capital T, they all have the same angular speed omega. But we can notice how this expression is actually part of this formula. So we can replace that with omega, and we come up with a very useful statement that the linear speed or angular speed depends on r times omega. Make sure you have written down any of these important equations from the slides. All right, well, that angular speed is not always the same. Objects do need to increase their speed to a certain constant speed or decrease that angular speed as they're slowing down. And in the same way, the individual points on that object will have a greater and greater linear speed and then a decreasing linear speed as it slows down. So we can talk about an acceleration, a linear acceleration or tangential acceleration, as well as the angular acceleration. So the tangential acceleration is denoted by a sub t, and it describes the rate at which the tangential speed changes, measured in meters per second or meters per second squared, just like any other linear acceleration. And then let's take a look at the mathematics of this. The pattern is actually very similar. So if v equals r times omega, then our linear acceleration a sub t equals r times alpha. So again, very parallel formulas. Look for those sorts of patterns as you're working.